Here is our Tesla turbine setup. On the far right, you can see the turbine itself and the sensor that runs underneath it to detect RPM. That sensor is hooked up to the Arduino, which turns the RPM into a 0 to 5 volt signal, which runs into the PLC. The PLC program then tells the valve controller whether to open or close to maintain RPM from the turbine using a 4 to 20 milliamp signal. The controller then opens or closes the valve as needed to maintain RPM, which is at the top of our setup hooked up to shop air. Here is our turbine in operation. As you can see, everything is hooked up and running. Over here, I'll change the set point to 30 and you will hear the RPM drop and the air turn off. And here you see the RPM dropping. It will drop below the set point, but you can hear the air kick on around now and the RPM start to climb again, and it will eventually level off to our new set point. Here I change the set point again, and you can hear the air turn on and the RPM start to climb, and again it will go over, but eventually level off and you'll hear the air kick back on. And here are our parameters. Here we have the set point, the error term, our loop algorithm, our output, and our process variable. Here we are applying a brake force to the turbine. Looking at the code, you can see the PLC's reaction to the braking force, where the output rises and the RPM reaches that set point again. Here we are applying the brake force, the output goes up and the RPM goes to match the set point. To go a little bit deeper on how the system was tuned, we use the Ziegler-Nicholas method, which is a closed loop tuning method, which allows you to use the ultimate gain value and the ultimate period of oscillation to calculate the proportional gain. It is a simple method for tuning PID controllers and can be refined to give better approximations of the controller. And then the Arduino itself sends out a PWM, which is a technique of digital signal that is used to mimic an analog signal by changing the time between pulses while maintaining a mixed frequency. Right now we have our system in oscillation. By using these values, our proportional gain is set to 40, integral gain is set to 6,000, and our derivative gain is set to 0. You can see it's in oscillation and is oscillating about every 4 seconds. Using those numbers, we use the Ziegler-Nicholas method to calculate our values for the proportional gain, integral gain, and derivative gain. Applying those values, you can see that our system starts to rest. And we can change the set point as well. And we'll change it again.